So today's lecture is going to be about planning and multi-step reasoning. So today's lecture, we are going to cover 3 papers on multi-step reasoning and planning. Let's start with this paper from ICML of last year. So the title of the paper is Language Agent Tree Search Unifies Reasoning, Acting, and Planning in Language Models. So the target, the types of applications that we want to target in multi-step tasks are tasks that we not only need to reason about things, but also need to act through those reasoning steps and kind of search our trajectories or optimize trajectories on how we get to a final correct answer. So in the reasoning step, the model needs to think about what needs to be done. For example, what the budget is, where the plan is. These are the reasoning steps for a trip or vacation planning prompt. The act is, okay, now that you have certain types of reasoning or thinking, how do you kind of gather more information or act on these reasoning steps? For example, the action could be a browsing the web, generating a query to search, read Reddit or a travel blog, and so on. And then another step is search. Given these feedback or the information that's gathered online, how can we refine our plan so far? Maybe we can consider alternative destinations, search new things to do while we are there, and so on. So there are a series of reasoning, action, and search steps that needs to be done to solve this problem of, for example, planning a trip. So the problem or the challenge that this paper specifically wanted to address was the following. The goal here was, let's go from the LLM, generate a plan, and like executing on that plan to really try to encourage diversification and exploration of different types of plans or paths that the model can take, because models, and this is true still to this day, that they can be weak in creating a diversity of solutions or acting upon them and planning multiple steps of optimization to reach a solution. So this paper focused on bringing known techniques from reinforcement learning and multi-step planning that existed in the past, including multi-step Monte Carlo Tree Search, into the LLM reasoning path. And given that the models can take feedback in, it also introduced ways for the model to take different feedback as the model explores with the environment and bring that back in order to refine and optimize future plans and search processes. So just a quick kind of example of how this worked. For example, the prompt is to plan a trip to Hawaii. There are different ways and different actions that the model can take. So it can, for example, if we sample the model for this prompt, the model might decide that we might consider asking friends that already went to Hawaii or read subreddits related to that. And then this framework introduced a mechanism for getting a score for each of these actions, and then kind of update the search space or the trajectory of follow-up kind of expansion of this tree that is being formed based on that score. So in this case, and we talk about how these scores are generated. In this case, action 1 has a higher score, so we expand that action. So the model expands that action. So in this case, ask 2 friends about friend A and friend B about opinions, and then based on the quality of responses, there's score for that, and we can follow on from the model can expand from there. So there is a flavor of multi-action sampling in this case. The actions can be, in fact, be executed in parallel, like these two actions or these two actions. They both can be executed in parallel. And there's this notion of like, let's do continuous exploration based on the best state, but also consider a mix of exploration and exploitation. And that's where the MCTS comes in. So there are two kind of papers that this paper was basically saying how it diverges from those. Matt Shepard is a paper that we saw previously. And in that paper, there was a verifier that was guiding the search process in the test time. Basically, the reasoning kind of trajectories are scored by this verifier, and then the expansion is guided by that. But in LATS, which is this paper that we are going to learn more about in this lecture, the scoring is not based on reasoning choices, but it's based on the outcomes of the actions that the model takes. And also there is this part about reflection of the model to kind of evaluate how this trajectory went, and also about the observations from the environment. It also improves based on previous methods, frameworks and reasoning, such as the React work, where basically in React, there is this extra step of, we're going to see how this works, but there is this extra step of kind of memorization and again reflection and an interaction with the environment that we have in the LATS paper. And specifically, we have more and more planning into the process. So here is the intuition behind LATS. There is the chain of thought, where the reasoning process is basically decomposed into a number of steps. There is this notion of tree expansion. Basically, through this types of actionings, that action generation that we have a tree, that we form a tree and we do search and planning through that. And then we have this kind of like borrowed that from the React framework, where the feedback from these actions are incorporated into this search process for the future search and so on. So this method concretely has 6 types of kind of stages: selection, expansion, evaluation, simulation, backpropagation, and reflection. So let's see exactly how this method works. And let's walk through an example prompt. So in this case, the prompt is navigate through a maze to reach an exit. And then the initial observation is that you're in a dimly lit room. There are 2 doors, one on the left and one on the right. And the goal is to reach an exit in this case. So let's see how these different steps of LATS come into play. So first is the selection process. In this step, we need to select a node to expand. Let's say we have done that. We see exactly how that's done. But given a node, we want to see what kind of actions we can, given that we have selected a node, and this is based on UTC, we are going to see it in a bit. We want to see what kind of actions that we can take from that node. So in this case, our initialized node is this thing. You're in a dimly lit room and so on. Now, let's say the model samples different actions here. In this case, 3 actions are sampled. One is open the left door, open the right door, and the third one is inspect the room for clues. Then the next step is each of these actions are executed in the environment, and the observation is kind of basically appended to the context. So in this case, say if the action is open the left room, the observation is dark corridor with paintings. Action B is open the right. There's another observation, and so on for action C. Now comes the evaluation. So let's say we have an action, we have executed an action, we want to evaluate our new state that we are going into. For this part, they suggest averaging for creating a score based on the current kind of action and the observation. They suggest adding up two scores together. One is using an LM score, basically using LLM as a judge and prompting the model for evaluating how promising this state is, and literally asking it to give a score based on 0 to 1 for this state. And the other one is the self-consistency score. And that is, let's assume instead of 3 actions here, we had sampled 50 times. We had sampled 50 actions, and we categorized them into different types of actions. And if an action is sampled more, we kind of give a score, we give a score corresponding to the rate or the frequency of an action being sampled. So in this case, the self-consistency score for state A was higher because 75% of the time, maybe the action A was sampled. So the way to create just one value for this action is to add up these two. So now we have a value for action A corresponding to state SA. And then we have the simulation part. For example, in a greedy method, from the previous stage, we have SA having the highest score, SB and SC have much lower scores. So we go and expand SA all the way. Again, we can continue this process. We sample more from SA, and we continue expansions until we reach an end state, or whether it's successful or it fails, or until we reach a maximum, the budget that we have for expansion of this state. So in this case, from state SA, so this was SA, and then we have the candidate actions that start from that state. And then in this case, it's greedy. It takes one action, approach the staircase, and then we reach an observation, which we are lucky in this case. We have the exit door clearly marked. We got a point here. And then let's say the simulation is done. We either have a successful trajectory or it's a failure. Then the important part here is how do we use this observation to kind of backprop and update the scores that we had for different actions that were taken. So this is the backprop stage, and then that is used to influence the score of each state, and we're going to talk about it in a bit. Okay, let's talk about how this value function and backpropagation is used. So for the value function, we already saw that is a weighted average of asking an LLM as a judge, given this observation, this action, what are the chances of success? Give us a score between 0 to 1. And then there's the self-consistency, which basically we just count how many times a given action is sampled. Then there is the notion of UCT, or upper confidence bounds applied to trees. That's something that this is basically the number or score that is used for selection, because we have at each point we have a range of values that we want to see which node we go and expand. So the way UCT works, and this is completely borrowed from the MCTS kind of literature. The way it's designed is to try to balance between exploration and exploitation. If we just go based on the highest value at that point, we might miss out other nodes that right now, maybe at the current moment, have a lower value, but down the road at the end might have higher value. So let's balance the two of them. So the way UCT works is that it has this exploitation one, which is V of S, plus a hyperparameter times this other term, which encourages exploration. And the way this works here is that the NP is the parent, the number of times a parent of a node is visited, and NS is the number of the nodes that this current node is not the parent, but the current node is visited. And basically, think about it this way. relative to the parent node, if a node is visited less, we want to encourage visiting that node more. And if that node relative to the parent is visited a large number of times, then this number, this division, this becomes a smaller number, and UCT becomes lower relative to unexplored kind of children of a parent node. So UCT, again, is the number that we use for expansion, for selection of a node and going from there. Now, backpropagation, and that's where we go at the end of a trajectory, either we succeed or fail. The return of that trajectory is used to update the values, and this is like backpropagated through the steps. So at each point, the value of a state is the value of the old state times the number of visits to that node, -1 plus the return divided by the total number of visits to that node. So that's how the math behind this framework. Yes.
For the UCT, why does the have like one take or log, or one didn't take log? Like you take a log for the parent, but you didn't take log for the.
It's just something. There's some math and theoretical intuitions behind it. There's no proof that this is the optimal round, but you want to just balance the two in that like this is considered a more optimized way of doing things. Yes. So once backpropagation is done, they also append this reflection of the model itself about the trajectory that was expanded. If it fails or if it succeeds, the model adds some thinking behind what happened, what led to the failure or the success of this trajectory. And this apparently has been very helpful in overall increasing the quality of this approach. So they tested this approach on HotpotQA, which is some data set that we still we use it for multi-step reasoning optimization. Basically, the way this data set works is that for each question, for answering them, you need retrieval from at least 2 like different Wikipedia pages because it's just designed like that. So you need this multi-step by design kind of a process in order to find an answer. And they're doing really well. Like just look in terms of like as they increase the number of samples or the number of trajectories that they sample, they can significantly improve performance. And the reflection and bringing those kind of reasoning traces also gives a lot of boosts at the end to the model. So basically, they have provided a mechanism to translate more compute at test time effectively to better kind of solutions for these multi-step reasoning tasks. They also tested that on WebShop, which is this interesting data set for practical applications. There are, this is like, just to show you an example of how this data set works. For example, I'm looking for a small portable folding desk that's already fully assembled. It should have this color and this finish and so on, and the prices. So it's by design, it's a very multi-step process, and they're showing that their approach without any kind of fine-tuning and just at test time, they can get really high results, even close to human experts in this case. So to summarize, what Latz proposed was a new technique for kind of bringing in reasoning, taking actions and planning all together, and kind of brought in our known ideas like MCTS into the language model world. And they got very strong results on multiple domains. And given their test time approach and the modular approach, it's very portable and relatively easy to create. The downside, of course, is the cost. Each of these kind of like backpropagation and like expansion of a tree, all of those are adding a lot of cost, and the cost benefits was not really analyzed in the paper. Another assumption that this paper didn't address was really that there are scenarios where taking an action may be irreversible. So that's going to be challenging. Like, how do we adapt to those scenarios, right? If, like, for example, the model is running a transaction, like if it actually takes those actions, it could be very consequential, like paying for a service and so on. So that is another scenario where this approach might not be adaptable to. So here, there are a few questions about this paper that I really would like you to think about it, maybe for a couple minutes, and then we discuss anything related to where you see the strengths or weaknesses of this paper, or if you were to adapt it or extend it, how would you do that? So let's start doing that, and I'll get back to you in a couple of minutes. All right, let's get back. Anyone wants to comment on this work?
So the UCT method, it's basically like upper confidence bound, like from like banded learning setting, right? There's other algorithms for like picking, like in banded learning, like picking and exploring various arms. Did they try like different ones in this paper?
Okay, the question is UCT is one way to create this exploitation, but there are a lot of literature. No, whether they compared.
Yeah.
No, and there is that whole literature of multi-arm bandit and other ways that we can bring in exploitation into the optimization process, and all of that could be also explored here. They just I think their main contribution is that created a platform that now others can bring in other approaches to optimization. Yeah. Anything else? Questions or comments? Okay, let's move on to the next paper. Yes, go ahead.
If we were to keep track of the action trajectory based with the Monte Carlo Tree Search, what if there are times when there's like repeated actions, like action A, B, A, B, or when the same action is seen in multiple nodes? Is there any way to optimize this tree, or does this tree recognize all of these repeated actions as independent trajectories?
So the question is, if a series of actions are repeated, how do you... So the philosophy behind this is that if an action is repeated inside a trajectory, given a parent node, you would increase the count of that action, and that comes in the UCT formulation, right? So ideally, you would capture that as you are forming this tree, and ideally, this is a tree that you're forming, not like some kind of fully connected graph. So this is kind of the assumption behind this. Yes. So let's now talk about Spring. This is a NeurIPS 2025 paper, so this hasn't been even presented here at the conference. So this paper is about, again, gives you a flavor of this kind of planning and parallel execution of those plans, and how we can kind of use the model itself to enable it to think better in parallel, and we can optimize that. So this paper sprint was motivated by this observation that the reasoning models such as O1, Gemini 2.5 Pro, and pretty much all the frontier models right now, they have this tendency that for harder problems, they think more. And this longer thinking corresponds to higher accuracy. So we kind of like these models to think for longer and longer, kind of like chain of thoughts. For example, these two graphs here show that the DeepSeek R1 during the training process, as the training process continues, obviously it becomes better at solving these math problems. But also if we take a look at the average length per response, that is also going up. So it seems like there is a correlation between model thinking for longer and a larger number of tokens and the accuracy that we get from that. Now, again, so the observation here was that many like these long reasoning steps are helpful, but at the same time, many of these reasoning steps seem to be independent of each other. For example, the model tries alternative approaches. It decomposes a task into subtasks that some of them can be run in parallel. And then some of these steps are verifying the previous steps. So, but there is a lot of, if you look into the graph that describes a kind of the reasoning trace, there are parts of these computations that are independent of each other. So we don't need to really wait for all of these steps to be kind of created sequentially by the model. So we want to see how we can leverage this parallelism observation. And so the idea is we want the model identify these parallelization opportunities and kind of act on it. So Sprint is a framework that does come in during the post-training and or fine-tuning process. And what it does is that it takes a reasoning model and enables the reasoning model to execute like the response generation via a planner and a planner that creates a set of plans for how to approach solving a problem, and a set of executors. And those executors can be run in parallel in order to like carry out the plan. And this can happen again and again. We can have the next, we can have a plan, a bunch of kind of execution plans that are carried out in parallel, and then we can have another set of plans and then another set of parallel executions. So this the interleaving of this planning and execution is what it can enable acceleration of the reasoning process. So let's say how we can enable that, how we can enable the model to create these parallel kind of traces. And this is something that I want you to kind of think about it beyond just this paper, and we're seeing it in the following work that we are talking about. A lot of times when we want to kind of create data and figure out a certain behavior in the model, we can use the LLMs itself in the fine-tuning data creation process. And here is an example of that. Given a reasoning model, model's response trajectory to a question, we can decompose it in the number of steps via an LLM. So in this case, for example, we had DeepSeek R1 generate these reasoning traces and responses to these questions, and then we had a model like GPT-4o going through this reasoning trace and annotate the steps of the reasoning response. And not only that, for each of these steps, we ask the GPT-4o to annotate whether which part is the planning part and which part is the execution part. And in some steps, there were multiple execution pieces for a given plan. So, for example, we had this query, we had the reasoning trace, and then there are a bunch of things that needs to be done. And then when the reasoning stops, there is a final answer. Then we use GPT-4o to go through this process and kind of like create these steps 1, 2, and K. Basically, now we have these annotations. And within each step, the model also kind of annotates the plan and the execution. Which part is the planning part? Which part is the execution of that plan? Given that, then we can create a DAG of these steps. So we have step 1, step 2, and all the way. And we can, again, use the model. And the model does a really good job here of saying how these steps are related to each other. For example, the step 4 and 2 are not dependent on each other, but they both depend on step 1, is a follow-up to step 1. So now we have like a DAG of an optimization, and basically creating a DAG that describes how this reasoning trace works. And then we can do packing of these steps. For example, step 1 can be done first, and step 2 and 3 can be done completely in parallel with each other, and so on. And once we have these data set that we have annotated, then LRM here is just a large reasoning model. Basically, all LLMs are now inherently reasoning models. So what we are creating here is this data set of the steps, plan, and executions in parallel, and we basically fine-tune the model, for example, DeepSeek R1, to now think in that way. So previously, we would just create those, inherently have these properties, but now we want the model to think more and more in parallel by showing these parallel, like planning and execution traces. And we just fine-tune the model, in this case, just a supervised fine-tuning of basically showing the model the same stuff, the same thinking processes, but now annotated with these tags. And this helps the model that at inference time, now the model can output these tags. For example, here is plan 1, and then here are the execution patterns for this, and here is plan 2, and so on. So for example, for plan I, there is a set of thinking and the parallel execution that the model just outputs itself, and then we can kind of go over executing these plans in parallel and then syncing the output and returning the context. And then the model goes through plan I plus 1. And then there's a number of parallel kind of sub-plans within that the model can output, and we can go from there. Why this matters? So the cost of LLM inference, especially when we get to multi-step reasoning, becomes a huge burden. And you might have already noticed that yourself, when you spend a lot of time waiting for the model to output a response, it might make you kind of like not happy, you want the answers fast, but also it's a lot of cost and a lot of delay that goes into generating these responses. So right now, here is how the sequential reasoning models work. So there is a query, there is a plan, and then execution of that plan. There's plan 2, execution of plan 2, and so on. So this is the time that it takes to generate or like go over this thinking process and generate a final answer. But if we could kind of leverage this independence from plan 1 and plan 2, we could have the model we could have the execution of those plans be done at the same time. Here is what, after we fine-tune with the Spring at inference time, happens. So instead of model generating plan 1 and executing that, then generating plan 2, model generates these two plans first, plan 1 and 2, and then it starts executing. The execution of those plans happen at the same time. And then the execution could be using a tool. For example, the model is come up with a calculation, and then we can use this calculator or Python to execute plan 1 and plan 2 and so on, and then go to the next stage. And the fine-tuning data, again, this is another visualization of how, given these annotations that we have for plans and execution, we create the fine-tuning data. So we are basically asking the model to think in parallel if the plans are independent of each other. We are basically teaching the model to come up with plan 1 and 2 at the same time because they're independent of each other, and we execute them. Yes?
So if there's a need for replanning, how does the model remember which plans correspond to which executions and like all of those things, right? Like later in the inference stage, right? Like if after the execution of 4, the model realizes that, oh, what I did was wrong. How does it remember to like do a replanning of like go to the plan of 3 instead of like the plan of 2? You know?
So this work, I think you are kind of like bringing the previous work in here. Like here, the model can, so what we are teaching the model here is that to think about plans at each point of time, even if it's like a revision of an existing plan, if it can generate plans, if it can generate plans that can be executed in parallel, it should do so. It should not wait for the execution of plan 1 to generate plan 2, because plan 2 is independent of plan 1 anyway, right? So this is how we are creating this data set for training the model, to teaching it to think maximally in parallel and generate those plans. If the model wants to go back and reverse on a plan, it still can do that. It still sees all of these kind of contexts. It's just like the model is trained to think more in parallel, and also because it's trained to be like that, and we have these special kind of tags or ways of the model generating these plans and execution plans, we can act on it and enable, leverage those parallelism. Yes?
Actually change the structure of this LLM, because before you just need to predict the next token, but now you seem to have 3 parallel lines.
It's always next token. It's just that there is like, instead of like everything, the plan and execution one at a time, if there is a tag, like here, this is plan I, and here are the execution, and here is plan 2, plan I and I plus 1, for example, here's plan 1 and plan plus 2, this is the high level count. And then now that we know that there are these 2 plans, we can just branch out and run them in parallel. So that's the idea here. So here is the training recipe, starting from, so we generate 6K thinking trajectories for math data set. We keep the ones with higher parallelization, and we do supervised fine-tuning on DeepSeek R1, Distill Quant 7B on this reformatted trajectories. And the interesting property that we observed was that, so when we started the project, the goal was to maximize parallelism for reducing the sequential token generation, so we save on that. But it turns out this process actually helps out with accuracy as well. Like the model seems to like this kind of more structured way of thinking, and this way of encouraging parallelism helps the model have higher accuracy as well. And here what we are showing that is the average number of sequential tokens over the baseline model, like R1 distill 7B, and the sprint model again is distilling R1. This basically we are fine-tuning this 7B model, and there's a big jump, like a 3.5% jump over that, while also becoming much more efficient than a 32B model in terms of number of sequential tokens.
Like this accuracy of violence, or more opportunity to explore more approaches given the fixed compute budget. Because it
could be, yeah. There is, and we have some data on that, which I believe I'm going to show. Yeah, the model does explore more and think in parallel more. And another interesting observation was that we have out-of-domain generalization as well. So the thinking to training to think in parallel was done for the math data set, but we also saw the model is doing better, not only have more opportunities for this parallelism, but also higher accuracy for example, Countdown or GPQA Diamond data set. So there is no training, like we have not trained on those data sets, but the model generalizes. And this could go back to what you're suggesting, that the model can think in parallel. And that inherently seems to help the model. But as a side effect, we also have opportunities for leveraging this parallelism and reducing the number of sequential tokens.
Could there be a scenario where individually the answers are correct in the parallel branches, but when you combine it, say in a sequential manner, the answer may be wrong, and in that case, what will take precedence?
And in that case, but
what will take precedence? Because sometimes, even in a mathematical equation, individually when you look at them in isolation, the answer might look seemingly correct. But when you put all the steps together, the answer may eventually be wrong.
Yeah. So when the model generates no matter if it generates sequential or in parallel, at the end of the day, everything is condensed into the context. So the model sees that, and this is the thinking process. The answer after this, the model should synthesize a final answer. So if there are contradictions in the sequential or in parallel, the model is expected to resolve that before generating a final answer. So in that case, it's a little difficult to say because both approaches can be can suffer from kind of contradictions in the thinking. But here what we are seeing is more that like these plans are kind of like they're rather than being different approaches to solve the same problem, they're like different steps to solve one problem. Parallel. Another interesting observation was that, perhaps intuitive some, that harder problems require more iterative planning and execution. The other observation, this was like maybe less intuitive, was that in the early stages, so we have a bunch of these parallel planning, execution. In the early stages, the more parallelism or more exploration is observed by the model, and then in the later stages, we kind of converge to maybe less plans. Basically the exploration is more in the early stages, and towards the end we want to really go dive deep into a single plan and execution. Yes.
How can you ensure that the independent reasoning tasks are evenly load balanced and do not encounter bottlenecks? Do independent tasks, for example, have similar expected execution times?
Like here, you're saying that how do we make sure?
Right. So when we divide independent tasks, how do we ensure that these are going to be executed in about similar times?
So the question is, how do we ensure that these independent plans that are now run at the same time, they take similar times? So the thing is, we can ensure that, right? We have there are some kind of measures taken to enable that, but we still could have a straggler, like maybe step 2 versus 4 here. Step 4 may take a lot longer than step 2, but at the same time, we are kind of confined to just step 4, not step 4 plus step 2 runtime. And we have some measures. For example, if the plan if the execution is just too simple, we kind of merge that into the plan and try to create these bigger and bigger chunks that we can do in parallel. But that could be an optimization as well, the optimizing this across the stages.
I was wondering if there's a root analysis where reasoning tasks are functional.
I'm not sure if there are analysis exactly on that. Question?
Yes. Could you go back to the slide? So I saw on the math and GPQA, Spring has comparable accuracy and number of tokens as the baseline average. So I'm curious, for those benchmarks, what is the mean width of the tree, and what's the maximum width? In terms of because the width of the tree determines how much parallelism you can exploit.
So what you're getting at is that it's task dependent, basically.
Yeah.
The parallelism that we can exploit, and for some of these, if the ratio of the sequential tokens is for one task, for example, I believe for math is lower than for GPQ domain. Then yes, that's an indication of parallelism. Some tasks could be inherently more parallel than the other. And I don't know the exact number of the width of the tree here, but that to be able to leverage this approach, parallelism should exist. And but what we observed is that is the case for many of the reasoning problems like math and other kind of reasoning tasks in GPQA and so on. And some of these are, again, like for example, if you look at this for the math data set compared to some of these methods with like even lower but like comparable accuracy, we are increasing the bandwidth or reducing the number of sequence token by something like 40%, which is like a large number. But it is true that this is going to be task dependent. And maybe getting back to your questions, we have larger savings for problems that need more thinking. So, for example, here we are showing the sequential token reduction by sprint over the baseline, over the RFD model. This is the rejection fine-tuning methods. So this is another baseline that, this is a baseline we are comparing with. If the number of tokens generated, like in the thinking process, is small, then there's probably less opportunity for parallelism, right? So by doing this, like, oh, let's plan and execute, we can be worse than the baseline. But this appears in the harder problems and problems that require more thinking and more number of parallel tokens. And that's where this method shines and shows in parallelism. I'm not sure how many of you have read the recent Sonnet 4.5 system card, but it was very interesting to me that it says the prompt for the system card encourages the model to use tools as much as possible and at least 100 times. That's a very large number that the model is encouraged to use the tool. And this is like, just shows that we are going into this regime that we are solving more and more interesting problems, and we are actually going more and way beyond 8 to 10K even for the number of tokens that the model deals with for solving a problem. Yes?
If you come back to the fine-tune data set diagram on auto tools, fine-tune process. I did one. Yeah, they're doing inference. Does it produce the entire like step 1 to step K, the entire thing, but different layers? Or does it do a sequential?
No, during inference, it kind of just like this. So the model learns to generate plans that can be executed in parallel at the same time. So it first generates plan 1 and 2, and then once plan 1 is outputted, execution of plan 1 starts. Once plan 2 is outputted, execution of plan 2 starts. Then the result is put back in the context, and then the model is generating two more plans. So the model still takes this sequential approach to generating plans and execution, but with the difference is that if it kind of learns or is trained to, at each point of time, if there are plans that can be executed in parallel, it generates those at the same time. So here would be generates after step 1, it generates step 2 and 4 at the same time, and then you see the results for that, and then so on, and it continues. So think about it. Each step is a plan and a set of executions in the training. But the step here is defined as plan 1 and exec 1, and then it kind of changed the notion of.
Do they also match this? So let's say they execute 2 plans that can be parallelized, and then they collect the context, and then add it to the prompt for the next level. So they also do that in the training phase as well to match how they are prompting it.
Yeah, the training is shown here. This is how the training data will look like. So plan 1 and 2 are independent. So plan 1 and 2 are put together, next to each other, and then we have execution 1 and 2 during training. So that's how the model sees during training that plan 1 and 2 could be outputted together. But at inference, the execution is actually also done in parallel. Okay, let's move on to the last paper because I want to make sure we cover that. But just before that, opportunity. So here, the work did supervised fine-tuning. But of course, methods like RL and GRPO can enable potentially much more kind of benefit from this data and much more kind of this generalization property usually works well with RL. And other kind of notions about tool use, overlapping different tools, or like doing actually realizing the valve clock speedups is other work that can be done here in the implementation of this method. So now let's go through another method called SWiRL. This is also a kind of continuation of multi-step synthetic data generation and encouraging the model and helping the model do multi-step better. And this is a work that is going to be presented next week at Column in Conference in Language Modeling in Montreal. So this is another just a preview. This is another training, like we are using training and basically fine-tuning a language model to help it do multi-step reasoning better. So motivation, again, many real-world tasks require multi-step reasoning and tool use. For example, if you want to answer a multi-hop question using a search engine, you want to solve math problems, or solving a software engineering, like doing a project, planning a trip, analyzing data, and so on. Usually we go as humans, we use these tools and reason through them for like important tasks more than once. So we need a cohesive kind of number of steps of reasoning and tool use in order to solve a problem. So the challenges, again, in multi-step reasoning and tool use setting is that when you're doing reasoning and tool use, even for one step, it can get complicated. But as we expand on this and generate multiple steps of reasoning and tool use, the errors and the complications can compound over these different steps. If we want the model to, and another focus of this paper is enabling tool use, like teaching the model to use the right tools, for example, a calculator, Python executor, and so on. Using these tools live during the training process can be very challenging because tools can fail, they can be slow, and the training process is already kind of like time consuming and challenging, so this can further slow that down. And if you look back in terms of like the fine-tuning processes such as reinforcement learning from human feedback, from AI feedback, or execution feedback, many of these are optimized on the single step, are optimized for single step tasks. Basically, the model takes a lot of whatever it wants to do, generates a final answer, and the reward is just based on the final answer, whether it's correct or not, and then we kind of back propagate that towards actions. And here we want to have more kind of governance and kind of on the process of generating these steps and how we can optimize them. So this framework called SWiRL, and the design goal for SWiRL is the following. First of all, at a high level, we want the model to solve complex problem and multi-step reasoning tasks. We want the model to know when to call a tool, generate the right queries to invoke a tool, because we need to know how to use a tool, like the model needs to know that. Carry out these reasoning steps and maintain accuracy across them, and learn how to recover from error, and learn when to stop taking new steps and calling new tools and say, okay, I'm now ready to generate a final answer. So we want the model to know these steps. We also want to avoid using tools during the training process. Because like I mentioned, this can be slow, tools can fail, and can have bugs. We want to avoid that. And ideally, we want the model to generalize this. So ideally, we want the model to learn how to, when to adapt to new tools and new reasoning tasks and capabilities. So to approach this, here's the process. The first step of this process is that let's start with creating synthetic multi-step data for a model. So given a prompt, and in order to really annotate these steps, let's have the model take one step at a time and let the model know at each step that it's free to reason, create a chain of thought, call a tool, or propose a final answer. So having an input prompt, at step 1, we tell the model, you have access to these tools, you can generate a reasoning step. If you're ready to generate the final answer, just say that and create that. So given this prompt, the model would take the first action, which could be a reasoning step followed by a tool call, and then we show the model the environment response. So given that, then we ask the model again. We show the model again the same prompt, but this time we have kind of the context from the previous step. So basically we say, here is the original prompt, here is the previous action, and here is the result of taking that action from the environment. You can take a new action, which is, and call a tool, or if you're ready to create the final answer, just output the final answer. So by design, via this, through this adapt to iterative prompting, we are creating this multi-step data set. And the steps can be from 1 to 3 or 5, and so on for different queries. Then we need kind of a label. We want to have a notation of how good this step is. And to do so, we ask an LLM as a judge, given the prior context and the current action, which is a reasoning step followed by a tool call, give us a reward function, or give us like your estimate of how good this kind of trajectory and final action is. Given that we have, for each query and reason, we have a set of steps, and for each step we have a LLM as a judge kind of like score that is assigned to that step. And we can do that offline. We can go through many questions in parallel offline and generate these steps and labeled annotations. Once we have these steps per prompt, we can filter this data in different ways. For example, we can only keep the data where the judge, LLM as a judge, kind of decided every single step was a good kind of step. Every single action was good. Or we can go based on outcome filter data, and that would be we keep all the trajectories that the final answer was correct, no matter what the label per step was. And we're going to see how these two kind of differed with each other. But the whole kind of like intuition, motivation behind this part is that for these reasoning prompts, we have a number of steps. And then for each step, we have a reward created by the model, which we can use or not use during our training. But let's see how these two play out. Then, having this data that we have generated offline, we can start the training process. And this training in this part is done based on reinforcement learning. So maybe you can pay attention to this figure on the right. This is a very simple example, but let's go through that. Who is older, Glenn? Who, I don't know the last name, or Rosling. So these two people, who is older. So action 1 is to figure out who is older. I should first search for age of the first person. Then we have a reward for this action. We ask the judge, LLM as a judge, to say, given an input prompt and this action, what is the reward for this step? Then we actually go and show the model the result of this step, this is already we have in our training data. So we have the environment response, and then we prompt the model to take the next action. And in the next action is the second question, which is about the age of the second person. We have a reward based on that. And at the last stage, we say, given the result of the previous searches, we ask the model to generate another action. In this case, the model seems to be ready to output the final answer. So it outputs the answer in these tags, answer, and the final answer is there, and we can get a reward based on that. So the point that I want you to pay attention to is how we manage to not have the tool calls during training. So basically what we are doing here is that we have this trajectory from the prompt and from these kind of pre-designed, kind of collected actions and tool calls. During RL process, we get the reward, we show the prompt and steps and actions onto that action K, in this case, for example, up to action 1 and the environment response, and then we ask the model to take the next step. So this is the part that is done during training. The model takes the next action, but we don't need to execute that action or call the tool. We just collect the reward based on that specific action and use that for RL optimization. All the tool calls are just done during the data annotation process outside of the RL fine-tuning part. Because we realize that the model, the LLM just does a good job based on the quality of the action that's proposed. We're good in just evaluating that. We don't need to execute the action and evaluate that. So that's how we separated the two.
Do you need to train the LLM-judge?
We did not train an LLM as a judge for this. We just prompted, I'll talk about what models we used for each one. So there was no training for that.
But if the judge cannot see the real output from the full use, how can the judge well?
Yeah. So the question is, if the judge cannot see the output of the tool, how can it give a reasonable score? Yeah. So here's the point here. So we are asking the judge to judge the quality of the query that is generated by the model to call the tool, rather than the output of the tool. Like here, what the judge sees is that the model is asking age of this person, right? And the model can judge that this is a good kind of question to create for the search engine before seeing the result of the search engine, right? The model doesn't need to know the age of this person to know this question was good or bad. This is a good question. This is a reasonable question, right? So basically what we are doing is providing this process feedback, process reward for this step. And the tool calls are captured in the prior context. So all of these tool call results we have collected them in our offline training data set. We are not doing that during the actual RL fine-tuning. So to just show you the objective function that is being optimized in this multi-step RL is, let's say we have a number of steps, S1 to Sk, and then each followed by an action, which is a reasoning step followed by a tool call. What we are doing here is that we are optimizing the expected reward of an action, of a single action, given all the context so far, which is a set of states and actions that we have collected offline. So that's how we are optimizing the expected reward of an action, of a single action in a multi-step process, given all the prior steps. But of course, this varies from action 1 all the way to action K. Now, during inference, once we RL this model, let's walk through an inference process of how we encourage the model to do this multi-step process. So for example, here the prompt is, help me answer the following questions in just a few words. And then we specify the tool that the model can use, in this case, a calculator. If you think it would help to use a calculator, please generate a mathematical query enclosed by these kind of tags. And then we also tell the model, once you have enough information, you can generate an answer tag and generate the final answer. So through these tags, the model can tell us the tool call, or if it's ready to generate the final answer. So here is the input question. So in step 1, the model is prompted. Here is the input question. The model responses to that question. And in this response is calling it the calculator, and is calling this kind of like, this is the math that it wants to run. The user provides that output, like basically that tool is executed with that given input. We give the output to the model, and then the model is prompted again. Again, here is the input, here is the result from the previous kind of like thinking process and tool call, and the model takes the next action and next action and so far. So we are kind of iteratively prompt the model. Here is what happened so far. Here is the tool you have. If you're ready to generate the final answer, do it. If not, continue using the tool. So the experimental setup for this approach was the following. There is a GEMO227B was used to create this multi-step synthetic data. The questions were coming from HotpotQA and GSM8K. We had something like 50K trajectories sourced from a number of problems and created for different kinds of data that were, like I said, we can process this data that we created based on process filter, outcome filtered, both process and outcome filtered or random. And then we also corrected a number of trajectories, I think. So let's take a look at the impact of data filtering on the performance of SWiRL. One, perhaps in the beginning, this was non-intuitive, but we kind of realized why this is happening is that it seems like when our training data was only process filtered, meaning we took reasoning steps that were majority voted yes by LLM as a judge from the reasoning steps, but we kind of like didn't filter them based on the correctness of final answer. This seems to help the process more, the training more, than if we kind of rigorously only took trajectories where the outcome was correct or both process and outcome were correct. And the reason for that is if we only get trajectories where the model already knows the outcome and is correct, perhaps you're not helping the model solve problems that it couldn't solve during test time, because we are training it to think differently about these problems. So it can solve new problems that it couldn't solve before, but it had kind of gotten some processes correctly. But perhaps the most interesting, and this is again something that we are seeing in the Sprint project as well, is the generalization performance of the model. So, for example, we had SWiRL on GSM8K. These are math problems, and we were teaching the model to use like SymPy, a calculator basically, to solve these problems. So that was the training data. And then once we kind of do this multi-step RL optimization using GSM8K, we then tested on HotpotQA. And this is the accuracy that increase that we get from the base model. So it goes from 65 to 71. And if we were to use exactly HotpotQA, and in this case, the tool for HotpotQA was a search tool, not a calculator, the optimization, the increase was from 65 to 73. So, and vice versa, this was true as well. If we train the model on HotpotQA with a search tool, it could also do well on GSM8K with Python. So it seems like there is something going beyond just like learning to use a specific tool. Rather, the model is learning how to think in steps and learn how to invoke a tool. And this was perhaps, and these data sets, the other data sets are separate from any of our training data. Another important observation here was that, again, in this case, the model is being trained on HotpotQA using a search tool for all of these, but we are showing the test results as we are increasing this synthetic data, the training data size. So it seems like as we go from 100 training examples to 10,000 training examples, even at inference, the model is improving on a completely different task, which is math problems and GSM8K. So this is like, again, I think it's the most important graph from this paper, showing that by creating synthetic data in environments that are perhaps like easier to create these data for, and teaching the model how to use these tools and how to think in multiple steps, we can generalize these behavior to entirely new tools and domains. And perhaps scaling this up could be a very kind of powerful methodology. And here we are showing some results on the, like, to kind of try to interpret why the model is becoming better through this RL processes. And what we did here is to look into the average kind of process reward per step of the model in answering these questions before and after being fine-tuned through this reinforcement learning process. And perhaps this is, again, very intuitive that the process correctness of the model has improved throughout this process for both in distribution domain, where we train on HotpotQA, and out of distribution when we just tested on GSM8K. So the model thinks more correctly per step, both on the training data, but out of distribution data. And here are some other results that we can also looked into precision, recall, and other metrics across a number of tasks. Here are how this works compared to frontier models. Something that is perhaps is worth noting here is that we could do all of this process that we did with RL, we could do it with supervised fine-tuning as well. And it turns out that this multi-step RL does better by a good amount over supervised fine-tuning. And especially for supervised fine-tuning, it seemed like the model really benefited, like the training data needed to be correct, like both process and outcome filtered. Supervised fine-tuning on that kind of training data worked better than when we selected only the process filtered data. And it kind of makes sense because in supervised fine-tuning, it's kind of an imitation learning, right? We are showing these are the trajectories and we want the model to repeat those in a way. Whereas and then if they're incorrect, the outcome is incorrect, it might hurt performance. Whereas in RL, we are giving the model a new chance to take a new action given the prior steps. And we are kind of giving a reward based on that new action. And that's how it can break out from this. And here are some other results. But because we're out of time, let's just take a look at the summary of this. So again, an important observation was that SWiRL generalizes across data sets and tools. It transfers to disparate tasks, and the model learns better from process filtered data, and it can get a lot of gains from more synthetic data, both for in-domain and out-of-domain. And from just understanding why this happens, it turns out that after this sort of fine-tuning, the process behavior, like the process correctness of the model improves. So if we just go to evaluate that, the model becomes better at this multi-step thinking. Again, this is true for both in distribution and out of distribution data. And with that, we can conclude this lecture. I hope you learn more about multi-step and reasoning and planning, which is a very active field that is going forward.